Good morning, everyone. Welcome to the October Zoom Citrus Seminar. Thank you for joining us. First, I would like to thank Alison Walton from the Immokalee IFAS Center for her help and cooperation. Today's program offers 1 CEU for pesticide license renewal and 1 CEU for certified crop advisors. If you need CEUs, email me your name, email address, and license number. Our guest speaker today is Dr. Ioannis Ampatzidis, Associate Professor in Agriculture Engineering at the UF-IFAS Southwest Florida Research and Education Center in Immokalee. The title of his presentation is Artificial Intelligence, AI, Enabled Technologies for Precision Citrus Management. Artificial intelligence in agriculture. Its application in agriculture represents a big step forward in how we grow, harvest, and distribute food, influencing the farming community and society. It is also important to realize that there are disadvantages to technology in agriculture. AI's role in agriculture is substantial, particularly in increasing productivity. AI systems optimize farming practices through data collection and analysis, helping farmers make informed decisions about growing crops. By analyzing vast amount of data collected from sensors, satellites, weather forecasts, and historical crop patterns, AI algorithms predict optimal irrigation, fertilization, and pest management of crops. This predictive capability ensures better resource allocation, which leads to enhanced crop yield and increased productivity. AI algorithms also predict crop diseases, pests, and nutrient deficiencies. Early detection allows for timely interventions, reducing crop losses and the need for chemical treatments. The future of AI in agriculture should rely on a balanced strategy. However, AI can revolutionize farming and boost efficiency and sustainability in agriculture sector. Dr. Ampatzidis' talk will present current and emerging AI-enabled technologies for precision citrus management. Examples of these technologies include an AI-enhanced and automated trunk injection system, Agrosense, an AI-enabled data collection technology, smart sprayers and fertilizers for tree-based nutrient management, and a cloud-based and AI-driven platform, Agroview, to process, analyze, and visualize data collected from aerial and ground sensing systems. Dr. Ampatzidis, it is all yours. Please go ahead. Thank you.
Thank you, Mongi. Hi, everyone. I hope you can hear me well.
Yes.
Okay, you can still see my screen, right?
Yes.
Okay, so what I will try to do today is just give some examples of how we use AI and automation and robotics to enhance precision management of citrus. I'm not going to cover a lot of the, things that you guys know already. For example, like this is a graph for the citrus production in the last 20 plus years. And you see a huge drop because of HLB, citrus greening, but also because of extreme weather events like hurricanes. We see that after some hurricanes, we have significant damage and then reduced production. So first of all, HLB affected the production, like we lost more than 70% of the production, even maybe more. So it's a big problem, but also extreme weather events cause a significant problem to Florida citrus industry. So I will present some tools that we have developed, and we hope that we can use to help production of citrus again. So HLB, again, you're familiar with that, or citrus greening. You know that the bacteria lives in phloem. So recently, a lot of growers try to use track injection. And the idea is like to inject some therapeutic materials directly to the phloem or xylem, and then through the xylem it will go up to the tree, distribute, and kill the bacteria. So this is not a new idea. It's a pretty old idea. This is some examples of some devices that we currently use. Again, the idea is pretty simple. You need to create a hole, like the one that you see here in this picture, if you follow my arrow, with a drill. And then you attach a pressurized system, like a syringe, that, with low pressure, it will absorb the material and move it up to the tree, hopefully. Again, this process is simple, but it's very time consuming and labor intensive. As you can see, these two videos, you see some people with drills creating some holes and then attach this pressurized system. Again, very labor intensive, very time consuming. So back in 2018, we start thinking about and talking about this 17, 18. We're talking about developing an automated delivery system. So how, again, the idea is how to automate this manual process. And we submit a proposal, I think in 2018, 2019, it was funded by USDA. It was almost $3.4 million for 5 years. But it was not just to develop this technology, because we didn't know a lot about track injection. We had a lot of different tasks to identify when is a good time, for example, to apply, what chemicals to use and apply. I mean, all this critical information, I mean, morning against evening, different seasons, how many times per year. So we had a big grant, and part of this one, around $600,000, was for the development of this automated delivery system, which we found out that was not enough. And I will explain why. We have developed a lot of prototypes. As you can see here in the first video, we have this system that we punch the tree, and through needles, hollow needles, we injected some materials. In this case, you see, we turn it on just to see how it works. And then this is a different prototype. Actually, we have a handheld prototype. We have different prototypes. And then we had a lot of, we identify a lot of issues, which I will skip for now, but there, it wasn't an easy process. And then we designed the end effector several times. We thought that small needles will be sufficient. So the depth at the beginning, we thought it will be like half of an inch will be, or even less will be sufficient. We found out that we need more than that. Now we go almost an inch deep. So we had to redesign this system without, again, skipping these details. The same with the needles. We tried different type of needles. We designed the needles. As you see here, all these pointing type of needles create a crack. So we found out that was not a good idea. So we tried one that was rounded. And this is the hole that through this hole, we inject the material, whatever it is, the liquid material. And you see the dimensions of these needles. So again, a lot of developments, a lot of trials, a lot of problems that we had to deal with. But this is what we have so far. We developed this system. This is the latest prototype. So we use a position arm, and then we have the end effector, which is this system that pounds the tree and then create the holes, and through the needles we inject the materials. And you see the 2 needles now. We used to have 4, 2 and 2, but now we will just work with 2. I mean, still this is something that we can change and modify it if needed. And this is just a video demo to see how the system works. So again, the idea is to not use a drill to create a hole, because that's a big problem. So we punch the tree, and then through the needles again we inject. And this is again another video. As you can see, we punch the tree now, and then in all these figures, the x-axis is the time. The one at the right, in the y-axis, we have the volume. The mid one is the pressure, and then the flow rate, the first one. And also you see that the volume drop up here. So as you can see, we're able to inject 50 or 100 ml in less than 30 seconds with this system, which is a huge improvement compared to the manual system. You can see in this graph, the volume is going up. So the pressure is still low, and we believe that this is because the tree is able to absorb the materials at the beginning. So as you can see in this experiment, we keep going. I mean, you can stop at 100 ml, because this is the amount that we apply right now, and we apply in both sides of the tree. So as you can see, there's no leak, but we just want to see what will happen if we keep going. And then we are able to apply even 200 ml, and then you see the pressure is building up. That means that probably somewhere here you need to stop the application, the process, because the tree cannot absorb more, and then you see the flow rate going down, the volume is getting a plateau, right? That means, okay, I cannot absorb more. We compare that with the manual system. This is the automated system, and this is the manual injection. Don't worry about these details, different concentrations of a chemical, OTC, that we use right now, and water. And then this is the injection duration. So for the automated system, it's in seconds, this is in minutes. So the main difference here is that for the automated system, it took less than 20 seconds, 20 seconds to inject 100 ml of the material, even water, or 11,000 ppm 40C or 5,500 ppm 40C. And for the manual, it took more than 24 minutes. Sometimes it was hours, sometimes it was like 2 hours, sometimes it was 10 hours. So a huge improvement in the time. And again, with the manual system, they usually they inject, let's say in the morning, they create the hole again, they put the system there, and then they leave it for the entire day, and they go at the end of the day to collect all these devices. So with this system, we are able, again, to inject quickly, and also we believe that we make less damage. But this is something that we are still looking for, because this is, again, the hole from the manual system, because, again, it's drill-based. As you can see, it's pretty big hole that might create a problem. And then this small one that you cannot even see very well is from the automated system, because, again, we don't drill, we just punch the tree. So again, feel free if you have any questions to put in the chat, or even unmute yourselves and ask during the presentation. That's okay too. We have already published this work. My PhD student, and he already graduated actually, Dr. Israel Ojo. He was the lead of this project, and he has already 4 publications about this technology. So if you want to know more about it, more the details about the engineering part, the specifications, you can check out these papers, or feel free to email me, and I will share all these publications with you. Also, what we try to do now with this system is to fully automate that. So the idea is to add some sensing and AI, so we can be able to detect the trunk and the injection point, as you can see here. This is very important. And through that, control this robotic arm, the positioning arm, so to fully automate that. We already start working on that. We developed the sensing system, but not the control yet. And this is some initial trials of the track detection and just walking around with a camera, and we are able in real time to detect the trunk. And also we are able to detect the injection point. We cannot see that here, but even the location that we need to inject, that's very critical. And there's also a conference paper about this system, and we are going to submit a full paper soon with more details. But we don't have any other funding to continue this research. The project ends at the end of this year, and we put some proposals to USDA, also here local to Florida, and then none of them were funded. So I don't know how we are going to continue. We talked with some companies, private companies, that they are willing to maybe develop a product and commercialize it, but so far we don't know exactly if we are going to continue or stop here, which I hope to continue and commercialize it. But it needs a significant funding to develop something like that. The cost of the system is very low, the final product, but to develop it costs a lot of money, because it's a lot of fabrication, a lot of small things that we need to correct, and of course people to work and try the system in the field. So a different technology, this is something that we have already commercialized. There's a spin-off startup company that licensed this technology. We call it Agroview. The name of the company is Agricultural Intelligence. So the idea of this one was, first of all, to collect aerial data. This is how we started. Now we also collect ground data, but we started with just collecting aerial data, and then develop a software that can process the images, from example, images from drones, and provide some critical information to the grower. So again, back in 2017, I moved in Florida, and Hurricane Irma happened. So after that, a lot of growers, they want to assess the damage, but also just have plant inventories, right? Count risks. And back then, they used to hire people to do that. So they had to hire people driving in a truck or any farm vehicle with clickers, and then when they see a small tree, they click one clicker. When they see a medium-sized tree, they click another one. When they see a gap, they click a third one. So that was very, very expensive, very, very time-consuming. It could take months to create your plant inventory, to count how many trees you have. So that's why we start developing this technology. And this is an example of this around 2,000 acres farm. You see different blocks. So when you click any of these blocks, you see some initial analytics here, how many trees you have, how many gaps you have. You see that as a pie. Also, we develop, we estimate the nutrients, the leaf nutrient concentration, and we present down here from NPK, but also from micronutrients. And you see some publications from 2020. We have some other one from 2019 about this technology. So when you double click the field or click here, view block, then you go inside the field. So with all these green dots, there are the tree detections. So we have different smart algorithms that they detect the trees and collect information about every tree. So the information about the tree is the plant height, the canopy area, the leaf density. Also, we have a health index. And with the blue dots, you see here, all the gaps. In this case, the grower wants to count all the gaps because he wants to order new trees. So he came to us, and in less than a week, we were able to develop these maps for all these 2,000 acres, and he knew exactly how many trees to order. And this is a video demo of this technology. Again, it's a little bit older version of the system, but again, when we hover and click any of this block, you see the initial analytics. See how many gaps we have. The red color is the gaps. When you click view block, you are inside. Again, this is a very interactive system. You can select or unselect the trees. You can zoom in, zoom out. Again, different colors in this example presents different height categories. You see that in the histogram here. So you know how many trees you have, but also you can categorize based on the height, canopy area, leaf density, health. The blue ones are the gaps. As you can see here, we had a lot of gaps. You can see how many trees you have in all these different categories. You can change the bins, the categories from 2 to 9, I think right now, or to 7. You can even select to present, in this case, trees that are less than 10 feet tall. So again, very interactive. We have a Twitter that you can follow us, and you can see again all these videos and pictures or learn more about these technologies. And also we create these fertility maps. So again, using drones and multispectral imaging, we can create maps like that. This is very well-known maps for precision agriculture. We call them zone management maps. So every zone, every color here is a zone. So represent a different category from deficient to excess, and this is for nitrogen. As you can see here, we have a deficient zone, low, and optimum, and high. So, and when you click here, generate the report, we have a report like this one for every nutrient that we can predict. And you see for nitrogen, for example, we give also some suggestions, recommendation about what you need to do in different zones. And also the application rate, you can create through this fertility map an application map. So for variable rate technologies. So for example, you can select how much you want to apply in every zone. And then if you have a variable rate sprayer, which we are developing currently, or fertilizer, it will be able to change the rate in real time as it goes to these different zones. And again, we have already published these technologies. This is back in 2021. So another technology, Agrosense. So Agroview is to analyze data from drones mainly, but also for planes or satellites. And again, it's fully automated system. You can upload your raw images from the drone, for example, stitch them together, then you create the perimeter, and you have all the data, all the analytics. So Agrosense is a technology that we developed, first of all, to convert traditional sprayers to smart sprayers, but also it can be a standalone technology that you can put in any farm vehicle to collect data from the grounds. So now we need to connect the ground-based sensing, so data from the ground, from the data from above, like from aerial data from drones or airplanes, so we have a better understanding of what's happening in the field. So this is an example of a broadcast sprayer. So we have the nozzles here and a fan. This is a very common sprayer. What we try to do here again is to optimize that to control the nozzles. It can be divisional nozzle control, or it can be zone-based. And why I want to do that? Because in Florida, especially, we have a huge variability in the field. So we have, first of all, a lot of gaps. So you see here in this example, these blue dots are the gaps. If we have these gaps, you don't need to spray in this area, first of all. There's nothing there. It's a waste of the chemical, waste of money. Plus, also, there's a huge variability in the tree size, the volume. You can see small trees, very young trees next to a big tree. So that's why we try to optimize this one using Agrosense. Agrosense is able to detect the size of the tree, the leaf density, and the height and the canopy area. So based on that, you can control or individual nozzles, or you can control zones. So each zone might have, for example, 3 nozzles. So we can have 4 zones, for example, from the left side, 4 zones from the right side. So we start working on that back in 2020. The first paper came out in 2021. In the first prototype, we used a sensor fusion. Again, very low-cost system with 2 cameras and a low-cost LiDAR. So we had sensors on fusion and AI models running in real time. And again, we're able to detect if there's a tree or not, which is very important. If it's not tree, you don't need to spray. And if it's the tree, what is the height of the tree? And then also collect information about the leaf density, but also at the same time count fruit. And we have a second prototype now that we are trying a different approach. My previous postdoc, Konglen Zhu, led this project. And you see here that we have 4 cameras, and this is depth cameras. So they collect images, but also they measure the distance. And this is pretty important, and I will explain why soon. But we put 2 cameras from one side, 2 cameras from the other side. Again, in real time, we run the AI models. Again, this is a smart and low-cost system. So why we need the depth information? So you see here in the first set, in the first 2 images, they are the RGB images. They are the red, green, and blue, the images that you can take from your cell phone, right? But sometimes behind a tree, there's another tree. And even, we can have a dead tree, but in the background, if you have another tree, it looks like alive, it looks like green. So that's why we use the depth information to filter anything on the background. So you see in the second one, using the depth image, we can filter the background, all these big trees or whatever is in the background. And then we have, at the end, only the image of the target tree, which is, again, very, very important. Based on this image now, we can develop machine learning models, AI models, that will detect the height. I mean, the height is not from AI models, but the leaf density also, and classify that. So this is, again, 2 cameras from one side, 2 cameras from the other side. So using these 2 cameras, we're able to detect the height. I'm not going to technical details here. And also the tree trunk, as you can see in this image, even in this small tree. But also we are able to classify the leaf density. And again, this is information that we can add on Agroview, right? And this is very important because you can detect dead trees up to healthy trees. Healthy still HLB affected, but more dense trees. So we also develop a graphical user interface. So here, some important information is like you can change the buffer zone. This is how many inches you can trigger the nozzles before the canopy, because you need to spray before and after in order to cover the entire tree. But also another important information here is you can select to apply to all trees, or you can select to apply only to young trees or even to mature trees. Sometimes you just want to apply to spray on young trees. So you can select that through here, and the system is able to do that, understand what is young and apply only there. So this is a video demo of this technology. This is the first prototype. Sorry, let me go back. And if I pause it somewhere, pause it here. So the same time, again, we spray, we collect all this information. And also we count fruit. We detect and count fruit, not all the fruit, but this still is very critical information. And then we know the location, we know the fruit detected, and then we know the condition of the tree. The condition of the tree is, again, based on the leaf density. It can be at risk, dead, healthy, or it can be a gap, there's nothing there. And also the height. Based on the height, we can trigger the number of nozzles or the zones. And then as you see here, we detect the fruit, and then this here is a gap. So you see that the right side of the sprayer will stop spraying. And then the next tree, this one is at risk. Again, the sensing system is here. So what you see here is the video from the right camera. So here it's at risk, or now we have different density categories because we have less leaves. And then here you can maybe change the speed of the fan so we have a better coverage. So by doing all these things, we found out that we can optimize this application and reduce the use of chemicals by 30%. And that also depends on the variability you have in your field, which is significant. Again, to other videos, in this example, the first video, you see a gap in this side, we stop spraying, but this is a dead tree here. And if I pause it, like this is a dead tree, and you see that the system is able to detect it and stop spraying because you don't need to spray in dead trees. In the second video, you see at the turn, the system doesn't spray because there's nothing there. And then because we have smaller trees, it's more like on-off. And not all the nozzles are triggered, only the first zone. And also, this is a pole. It detected as an object, but it didn't spray. You see, the system were able to understand that, okay, there is an object there, but it's not a tree, so it didn't spray. And also at the end, we create spraying maps and fruit heat maps. We collect all the data in a USB stick that you can upload to Agroview, and Agroview visualize all the data. And again, the process is automated. So one important thing that I forgot to mention is like that Agrosense processes data in real time and stores only information, not the raw data, which is very, very critical. Because if you store the raw data, imagine that you have like images from the cameras or from the LiDAR, we have a 3D points. That can be huge amount of data. So you have even problem with storing the data and then processing later. So, but we don't do that. In real time, we process the raw data and we only save the information, which is okay, the detected trees, the number of, the height of the tree, the leaf density, and then information about the spraying applications you can see here. With all these dots, again, here are the GPS locations. When you click any of them, you see time, date, speed, flow, accumulated flow, and the number of detected fruit. Again, when you zoom in, different colors are different rates here, and you see more differences. But again, this was almost 500-gallon sprayer. So this is the start of the application. This is the end. And here the operator usually needs to stop, put a flag, drives back to this side of the row, put another flag and goes back, refills, comes back, and needs to identify the flag and continue from this point, which is sometimes they don't do that. And imagine if you spray for pest diseases, you cannot skip this area. But with our system, first of all, you can evaluate the quality of the job if you came back and continue from this point. But also we can develop a system to guide the operator to start from this point so he doesn't need to stop and put flags. And this again, the second image is from a fruit heat map that we already use to predict the yield using the data from drones and the ground data. We are able to pretty accurately predict the yield. It's more complicated in Florida because of HLB. We have also fruit drop, and that might affect the final yield. But we believe that with Agrosense, we will be able even to identify and detect the drop event, the fruit drop event. So a month before harvest, you might lose 30% of your fruit because of citrus greening. So, but if you go and let's say spray or fertilize, we usually spray or fertilize frequently. So if you go back to your field with any of your machines and you have Agrosense there, you will be able even to identify this event when that happens and even quantify it. So something else that we are trying to do now, we found out that, with drones, we get some very good information, but the cost is a little bit high or higher because the range is small because you need to go to the field, fly the drones. So there's some cost associated to that. So the idea here is to use some generative AI techniques. Again, I'm not going to be very technical. In super resolutions, the idea here is to use images from planes or satellites that they come with a lower resolution. This is the problem that, for example, Agroview needs less than 10 centimeter per pixel resolution to process all the data, to detect the plants and to get information about every plant. But the satellite can come to 2 meters by 2 meters, or in the good case scenario, 50 centimeter by 50 centimeter. The airplane can be 20 to 15 centimeter per pixel, which is still not that good for this precise analysis. So we use this a novel technology, a novel technique that we developed to enhance images. Christian Lacerda, he's back in Brazil. He was an intern in my lab, led this project. And as you see here, we took, this is an image from airplane of 15 centimeter per pixel resolution, the first one. And as you see, I mean, you can say, okay, this is a tree, but it doesn't look, the resolution is good, but also the quality of the image is not good. So we try with this technique to improve both resolution and also the quality. And as you see, this is the B is a different technique that we use, and the third is our technique, that we're able to increase by 4 the resolution to almost 4 centimeter per pixel. We still need to improve the quality, but it's a very promising work. And again, this is another example, this 1 meter per pixel resolution. As you can see, it's even very small. You cannot really zoom in a lot. And we're able to increase to something like that, to 25 centimeter resolution, which is much, much better. And then also here we have, to run all these models takes a lot of time, weeks. So I'd like to thank NVIDIA for donating a server through super microcomputer scenes to us. And that helped us a lot in order to run all these models. And again, we put all these now enhanced airplane images to Agroview to reduce mainly the cost. This is the idea here, not only the cost, but also cover bigger areas. And if we are able to do that with the satellites, we can even have data in a daily basis, or at least 2 or 3 times per week, which is very, very important. So here is just a comparison, just to simplify a little bit this table. What we did, we use airplane images, raw and plane images, 15 centimeters per pixel resolution. Then we enhanced them using our technique. We call it AgriGAN, the technique that we use from 15 to almost 4 centimeters per pixel. And also we use drone images, which is around 2 centimeters per pixel. So 10 different orchards. You see here how many trees were detected using the airplane images. This is through Agroview. So we took the airplane images with no enhancement and we put it to Agroview. And this is the results. Just 3 detections. And then this is through the enhanced, and then this is through the UAV. So the first error is the error between the raw images, unenhanced images, and the UAV, and the second error is the enhanced images and compared to the UAV. So you see that when we enhance the images, the error was like, I think the average was 4 or 6%. I mean, of course, we have from some of them almost 9.5, 2.6, 1.7, which is still pretty good by just using airplane images, because we are able to reduce the cost from $6 per acre. $6 per acre is the data collection plus the processing. We use cloud computing. So with drones, we estimate $6 per acre cost to 2.5 using airplane images, which is almost 3 times less, which is again pretty significant. And we're still working on that to see, because one thing to improve the resolution, the other thing is improve the quality, which is also very, very important. In another study from my postdoc, Caroline Tredin, we try also to evaluate not only the accuracy of Agroview, but also the precision. That means how consistent are the results. So if, for example, if I fly with a drone today and tomorrow and the next day and the following day, do I have the same data? For example, the tree counts are the same, the gaps are the same, the health index is the same. So this is very important because, you know, if the data are not consistent, that means, yeah, your system might be accurate, but the accuracy sometimes might be 90%, the next day might be 80 or 70, or other times might even be 110. So overestimate. So this is what we did here. We flew in 4 different dates next to each other. And then the first graph, you see the inventory. There are 2 different fields. And then different colors are different dates. So what we want here to be consistent. And for the inventory, the number of trees, we had a very small error. I think was less than let me see, less than 2%, 1.5% of the error. For the gaps also, you see they're similar. The gaps was a little bit a bigger error, but because we didn't have a lot of gaps. And the same for the second field. The first field I think was 2.6 and the error, and the second one 1.5. For the now the age here is not pretty accurate, but based on the height, we try to understand if it's the volume actually, if it's a young tree reset, or we have 3 categories, or mature, or something in the middle. And of course, we had some bigger error here. Like the error it's 6 to 8%, but this is expected because this is not a very well-defined metrics, the age. For the health, again, also it was pretty consistent, and we had based on our categories, we had I think 3 categories, but there are some trees in the limit that can go up and down. But I think the error there for the height was around 6%, which is pretty good. And for the big trees was 10%, which is a little bit higher, but still for what we need, it's a pretty good results. Health, again, also you see some good consistency here, how many trees are dead, at risk, and healthy. The canopy area, also we had an error of, I would check, of almost 8%, which is still okay for both fields. And the leaf density also, we had, this is not a, again, very well-defined index, but we got some pretty consistent results here too, with an error of 6, 7, and 14% from the different categories, which again, from what we need this system, it's pretty good. And I'll stop here. Thank you again for your attention, and I'm happy to answer any questions if you guys have any. And let me say also that we are looking for collaborators. If you are a grower, we are more than happy to come and use our technologies in your fields, and then we get your feedback and see how we can improve them. You see my information here. So feel free to call me or email me, or even use our Twitter to see, to learn more about the new projects that we are working on.
Thank you, Dr. Ampatzidis. Is there any question?
Let me say that for the track injection also we are We are testing the system even now. I mean, the project is going to end by the end of this year, and we don't have funding to continue, but we really want to see if we can commercialize it. So if you guys are interested, let me know. And then we can we are planning to develop a field day so we can demonstrate this technology. Still, it's a prototype, so we need to improve it for large scale applications. That's why also we are looking for some funding. But if you think that if you are interested, please contact me.
Again, if you need CEUs, send me an email. Thank you, Alison.
I think we have some comments.
You're so welcome, Mongi. We just got a chat in.
Yeah, we have a question about the craft block grant program, the craft. No, we don't work with them. There's another company, Aerobotics from South Africa, that they pick them and they work with them. But we also submitted a proposal to them, but it was not, we are not selected. And the second question is, what components of the trees in the smart tree crop sprayer are you using? Okay, so with the Agrosense, this is the sensing system for the smart sprayer. So what Agrosense does is, like, first of all, it detects if there's an object there or not. Then it can understand if the object is a tree or something else. So if it's just a human, it will not spray. Again, if it's a human now in front of the tree, it might spray, right? But if it's a different object, it will not spray. And then collect information about the tree. And then what information is that? First of all, you can count all the trees from the ground. To do that now, we focus more on detecting the trunk, which sometimes is not able to see, but this is how we detect trees now. So we detect the tree trunk and then measure the volume of the tree, which is the height and the canopy. We cannot measure exactly the canopy area, but we measure the height, which is very important for the sprayer because you know how many nozzles to trigger, and also the leaf density, which again, this is very important information, not only for spraying, but in general to know how many healthy trees you have, more dense trees, and how many weak trees do you have. It's very important. And at the same time, again, we count fruit, not all the fruit, only the fruit that we can see. But again, this is very important because you can use that in machine learning models to predict the yield, even months before harvest. And we have another question from Kristen about the AI models. And if we develop them, so we develop everything from the hardware part to the software. So all the AI models is not, for example, Agroview, we don't use only AI models. It's more advanced than that. So we need to understand the structure of the field. Every field has a structure, has rows, and then we need to understand the orientation of the row. All that information is very critical because you know where to look for trees. You don't look for trees, for example, between the rows, because might be there are weeds or something else that looks like a tree. And if you just run an AI model, it will detect trees everywhere. You have bigger errors. So it's more advanced. But yes, we develop all the AI models. We develop the sensing systems. We use cameras from commercial cameras, but we put them together, use microcontrollers, and in real time we collect the data. So we do everything by ourselves. And the mixed crops, I think you mean we have different spacing, or if we have high grass. So we have, this is a good example. So we have a lot of orchards that they are not, the spacing, the distance between the trees is not consistent. So when you have a dead tree, growers can go back and plant maybe 2 trees there. So you have 2 trees instead of 1. So that can change the spacing, but the system is able to even to detect that. That's why we detect individual trees. That's the goal. First is to detect the tree, and then the height of the tree, and based on that controls the amount that you spray, the nozzles, for example, how many nozzles to trigger. So Agroview from the drone is the same. That's why I say the system it needs to be smart or smarter than an AI model. So it needs to understand the different spacing. And if you have a lot of grass, that can be a problem. For Agroview, for example, if you fly from above, even if you have a dead tree, but it's full of grass under the tree, it looks green. So we try to develop filters, let's call them filters, to understand that, but it's not always easy. For the sprayer, it's somehow easier to detect that because you take the picture from the side. But again, it depends. If we have a small tree, we have a lot of cases that we have some small trees and it's full of grass around it. That will create some problems, and sometimes you cannot even see the tree trunk. So we try to see how to solve that. But that's why we have all this error that I presented. It can be like 7%, 4% because of situations like that. We test the system in real commercial groves, not in ideal situation. And if we work another type of crops, yes, we work a lot with vegetables. And we have different technologies for vegetables. I didn't present any of that, but we work a lot with tomatoes, even peppers, watermelon, from precision sprayers for weed management. So it's this idea you see and spray only on the weeds, not on the crop. This is in vegetable production. I have another PhD student working on that. Also for disease detection, using drones and multispectral cameras, we're able to early detect diseases before you see symptoms. We don't do disease detection in citrus because HLB is everywhere, first of all, and it's more complicated because you have HLB and then maybe citrus canker and black spot. So we know that the tree is not healthy. Another question is in terms of precision. So if we, okay, this is a good question. So if I understand correctly, you ask if we use time analysis. So if we can collect data, past data, to compare, and then yes, Agroview can do that. I didn't show that, but if you have, let's say, I had an example, but it's not here. But for example, we had 3 flights in 2 years, and 3 flights from drones, and you can see the difference. Actually, was one of the trees that I told you that the grower want to count how many gaps he had. So you can see, for example, in 2019. We had 2,000 gaps, and then June 2019, and then June 2020, the gaps were like only 50. So you had more young trees, and you can see we have a table that can detect this difference. And that's why we need now to use airplane or satellite imaging, because if we are able to use, for example, satellite imaging, and we can enhance it and use it on Agroview. So far, that's not, we are not able to do it with satellites because they don't come with good quality, the images and resolution, the one that we need. If you have 10 by 10 meter resolution and 2 by 2 meter resolution, you cannot detect individual plants, individual trees. So, but if we are able to enhance the images and Agroview be able to work on these images, then it can totally change the game. So because you can have data almost, as I said before, like 2 times per week, even daily, but let's say 2 times per week or 3 times per week, and then you can really compare and you can see differences. And actually, this is what we are doing, and we are putting in a new proposal to even detect damages from hurricanes. So we have data before and after, and with drones, we had another grant and we are able to do it from USDA. We are able to detect the fallen trees. It has to be fully fallen, but flooded areas and things, even to detect the long-term impact, which is very important. The long-term impact means that 6 months down the road, some trees might die because you had a flooded area. It's not only they might look healthy the next day or 3 days after, but like might die later. So this is important also to count, and we are able to do that. But now we need to see if we can do it using satellite or airplane images to reduce the data collection cost. And if we can detect ICP, yes. We even with Agroview, even Agrosense, both of these technologies, we trained AI models to detect trees that they were covered with a net. So this is, with the young trees, we cover them with the net to protect them from the psyllid, which is the insect that transfer the bacteria, the SLB. So we developed our models that they can also detect these trees. So now we might not collect good information, so accurate information about, for example, the height or the canopy volume. It might be that accurate, but we can count all of them and detect all of them. So the system, both Agroview and Agrosense, are able to detect trees covered with this net. Mongi, I can talk forever. I don't know if we have other questions or if you want to. It's 12. If you want to stop, or I can keep going.
It's okay. If we have questions, we can answer them. Any more questions?
Again, feel free to email me if you guys have any other follow-up questions, or even if you want to collaborate. I'm more than happy to work with all of you.
Thank you all for your participation. Thank you, Ioannis. Thank you, Alison. And we will see you next time.
Thank you. Awesome
you,
job,
Matthew.
Dr. Ampatzidis.
Thank you, everyone.